welcome everyone. Thanks for coming. So I'm Jonathan Dordick, the Vice President for Research here at Rensselaer. So increasingly, computational science and engineering are to research in every field as soil is to plants. It's the materials necessary for the growth of what we all do here. So as a result, our entire research community, everything we do on the research side and the pedagogy will benefit enormously from the strengths in digital disciplines that include high-performance computing, web science, data science, network science, cognitive computing, and immersive technologies, which this location we're here today is one of the, if not the, world-leading facilities to do just that. So these strengths are not just intellectual, but they're also infrastructural. Critical research platforms support Rensselaer's power in these digital disciplines, including the Supercomputing Center at our Computational Center for Nanotechnology Innovations, the IBM Watson Cognitive Computing System, our Center for Biotechnology and Interdisciplinary Studies, as well as the Curtis R. Preem Experimental Media and Performing Arts Center, again, that surrounds us right now. Rensselaer has the people, the platforms, the programs, and an expanding array of partnerships in place to shape the way the world uses its digital advances. The fact is testament to the leadership of President Shirley Ann Jackson, who over the last 14 years has really driven a lot of what we are doing here today, but also the brilliant researchers that I have the fortune to work with, that all of us have the fortune to work with here at Rensselaer. So in recent months, here at Rensselaer and around the world, including at the Royal Academy of London, where the President had an intriguing discussion where she articulated a vision of the ways in which new computational technologies and data-driven discovery and innovation will mold a new Polytechnic and change the ways universities collaborate to address large-scale challenges and opportunities. So today we take an important step towards realizing that very broad vision. And Dr. Jackson is here, of course, to explain and discuss that next step with us this morning. But first, let me introduce the President to you. Of course, many of you know her well, but I'll do a more formal introduction. So she has held senior leadership positions in government, in industry, research, and academia. Her research and policy focus includes energy security and the national capacity for innovation. She has addressed the quiet crisis of looming gaps in science, technology, and engineering workforce, as well as reduced support for basic research, something that we're all worried about day in and day out with what's going on down in Washington. Dr. Jackson serves on the President's Council of Advisors for Science and Technology, PCAST, appointed by President Obama in 2009. She is co-chair of the President's Innovation and Technology Advisory Committee, or PTAC, which is part of PCAST. She became president of Rensselaer in 1999. Under her leadership, Rensselaer engaged in an ambitious strategic effort known as the Rensselaer Plan that has transformed the university. And over the last year, she championed an effort and in fact challenged all of us to guide us towards a new refresh of the plan through to 2024 and extend our impact on humanity through forward-looking research initiatives such as the one we begin here today. So please join me in welcoming the 18th President of Rensselaer, the Honorable Shirley Ann Jackson.
Well, good morning, everyone. And thank you very much, John, for those kind words. Before I begin my formal remarks, let me acknowledge the presence of our wonderful County Executive, Kathy Jimeno. Thank you for being with us this morning. So let me begin. As many of you know, there is a significant transformation underway globally in the way we make discoveries, make decisions, make products, make connections, and ultimately make progress. And that transformation is being driven, as John intimated, by the extraordinarily rapid expansion in the availability of data from multiple sources and even more powerful analytical and computational capacity that is generating new information. So let me begin with a vignette to illustrate what I mean. Last fall, as Superstorm Sandy was beginning to gather steam in the Caribbean, 5 days before it slammed into New Jersey and New York, U.S. forecasters were predicting a monster storm, but they were uncertain of its path. By most indications, the unusually powerful and complex storm would graze the East Coast, but then move out into the North Atlantic. However, there were steady reports of the European model that predicted a sharp left turn into the coast of New Jersey and New York with potentially devastating consequences. Now, the US and European models eventually converged, but in fact, the Europeans got it right first, giving more time for those in Sandy's path to prepare, no doubt saving lives. Now, the difference in the early predictions lay not just with the inputs, but with the strength of the analytical models built on those inputs and the capacity, the computational capacity of the computers doing the modeling. Now, as intimated by what happened then with the Sandy forecast, newly available data and how it in fact is accessed, organized, and used will become an ever more vital force that shapes and changes our world. Big data-driven innovation and discovery will be drivers for changes in science and society during the next 50 years in much the same way as quantum science, which I built my career on, was to technological and economic development in the 20th century. Moreover, there is a rapidly growing network of networks, the so-called Internet of Things, on which our daily lives depend, including power, water, retail, financial, manufacturing, and social networks, all driven by the interplay of data, physical systems, high-performance computing, and analytical modeling. So big data and network science, in fact, are merging, marrying the Internet of Data with the Internet of Things. In fact, the Internet of Things generates data, and so that merging is occurring in new ways. And all of this will be world-changing if we can harness it. Now, in the 1800s, there was a shift from electricity as a curiosity to electricity being the commodity it is today, made possible by the emergence of the field of electrical engineering. And so we now are in the midst of a shift in data as a commodity, and importantly, data as a resource in ways not previously imagined. And so if we take full advantage of emerging technologies, new opportunities, then will come. And they will be created by the ability, with smart analytics, with sophisticated modeling, to anticipate and predict events, thereby making those events, particularly if they are ones that are potentially catastrophic, easier to manage. And so the intersections and interactions are complex. And interestingly enough, the outcomes obviously can be powerful, but also risky. Powerful in that we will be able to see connections that we would not have seen otherwise, and we will have better predictive abilities. But risky in that the interconnectivity can lead to unexpected results, ones we may not be prepared for, and can sometimes even be abhorrent, and certainly with unintended consequences, such as flash crashes in financial markets. Now, as we saw in such devastating ways with energy, communication, and transportation systems in the aftermath of Superstorm Sandy, interconnectivity presents enormous intersecting opportunities, but also intersecting vulnerabilities with potentially cascading consequences. Now, the level of interdependence of these interconnected networks will grow and will present even greater risks, but greater opportunities, again, if we're able to take advantage of the very interconnectivity of data and things that I'm talking about, and take advantage of powerful new analytical and computational capabilities and immersive technologies, as represented, in fact, by platforms like Impact, to stay ahead of the curve. As well, new economic and business models will emerge around data-driven information, both data at rest and data in motion. And there will be new opportunities, but with them, new tensions and potential conflicts around the monetization of data, particularly with respect to ownership, privacy, and security as these new models take place. And this then means that it's not just about the technology. It means that the intersection of science, technology, and public policy is important. So we live then in a data-driven, web-enabled, supercomputer-powered, globally interconnected world, interconnected both through the internet and through other technologies and through global natural phenomena such as climate-driven weather events. And this is a world whose technology Rensselaer Polytechnic Institute has helped to create. It is a world in which Rensselaer is positioned powerfully to help humanity use the remarkable technological tools at its disposal to answer the grand challenges surrounding energy, water, food, and national security, challenges that relate to human health, climate change, and the allocation of scarce natural resources. And therefore, today, I am very pleased to announce that we are creating the Rensselaer Institute for Data Exploration and Applications, or, as we call it, the Rensselaer Idea. Now, this university-wide institute will, in fact, receive $60 million in new investments by Rensselaer Polytechnic Institute itself, and over $100 million in total. Now, it will be led by a gentleman you will hear from shortly, Professor James Hendler, who is currently head of our Department of Computer Science and who is the senior constellation professor in the Tetherless World constellation. The Rensselaer Idea, this new institute, will bring together Rensselaer talents and strengths in web science, in high-performance computing, cognitive computing, data science and predictive analytics, and immersive technologies, and link them to applications at the interface of engineering and the physical life and social sciences. We intend to answer questions in nearly every area of endeavor and research that never could be answered in the past. And working across disciplines and sectors, our researchers will apply powerful new tools and technologies to access, aggregate, organize, and analyze data from multiple sources and in multiple formats. And in fact, that work has already begun, in order to address challenges and opportunities across the spectrum, including in basic research, in environment and energy, water resources, healthcare and biomedicine, business and finance, public policy, and national security. Educated in this context with new approaches and analytical capabilities, our students, the next generation of discoverers, innovators, and entrepreneurs, will be better equipped to truly change the world. Now, let me briefly describe and build on what Jim said to describe our talents and tools, and then say a few words about the ways in which the Rensselaer Idea will allow us to use them. In our Computational Center for Nanotechnology Innovations, the CCNI, we already have one of the most powerful university-based supercomputers in the world, whose capabilities are being significantly upgraded as we speak. upgraded this summer. And in fact, those capabilities will be astonishing by the fall. Stay tuned. And already our talents in the computational arena are shining through. This year, scientists at the CCNI, joining forces with the Lawrence Livermore National Laboratory, set a new simulation speed record in terms of a particular kind of simulation on the Sequoia supercomputer, decisively smashing the old record of 12 billion events per second with 504 billion events per second. So the point here is, it's not just the raw computational power. It is the ability to build sophisticated models, to do complicated studies, and to have them be executed at blazing speeds. Equally astonishing are recent advances in cognitive computing, technologies that are engineered for human-like ability to use natural language, answer complex questions, and make decisions. As you know, in 2011, the IBM computer Watson, which is a cognitive computing machine, using memory-based artificial intelligence, was able to beat the best human champions at Jeopardy. And this year, Rensselaer became the first university in the nation to receive the Watson technology. IBM chose Rensselaer as the place to send Watson to master a more difficult form of artificial intelligence, and that is knowledge-based artificial intelligence. And under the Rensselaer Idea, we will give Watson the power not merely to answer questions based on the subjects it has been taught, but also to access the tetherless world of information on the web and to make inferences from what it learns in real or near real time. That is one of the challenges we're taking on. Now, on the input side of the equation, the growth has been equally explosive, thanks to sources of data that now range from scientific platforms such as the Hubble Space Telescope to teenagers posting vacation photos on Instagram. The point is that the volume, the velocity, and the variety of the data collected from multiple sources, from social networking sites alone, should not be underestimated. In fact, in November of 2012, Facebook said that it was warehousing 0.5 petabyte of new data every single day. You know, it's so great to talk to a Rensselaer audience. I don't have to define what a petabyte is. And so the only reasonable explanation is that data genesis will continue its explosive growth, given that the existing internet is merging with the Internet of Things as the systems of our physical universe, our electric meters, our cars, our farming equipment, our houses increasingly are equipped with sensors and are networked digitally. As a consequence, data has been growing, in fact, at a volume much greater than the tools available to process it. But new tools are being engineered that enable us to take massive amounts of structured and unstructured data, manipulate them, and create useful information. We are developing advances in infrastructure that will allow us to access and reduce the crushing volume of unstructured data from videos, tweets, photos, posts, articles, papers, trades, purchases, and data from all sources of all kinds, including distributed sensor networks, satellites, et cetera, and create knowledge frameworks of data about the data. And that's what our folks in the Tetherless World constellation, in fact, do, Jim and Deb and Peter. And it's called Metadata, and that offers useful information about the world around us and allows us to build inference engines. Now, Professor Jim Hendler is, in fact, one of the originators of the semantic web. I didn't use your Playboy shot, Jim. And the semantic web uses common data formats for unrelated data sets, allowing us to have a new ability to integrate different sources of information, to search across them, and to visualize and analyze them. And that's what Peter and members of the Tetherless World constellation are so good at. Now, during the past 3.5 years, in fact, and it's probably outdated by now. The number of U.S. government data sets on data sharing sites has grown from about 57 to over nearly 500,000, I would say, and to more than 1 million data sets from governments worldwide. And Dr. Hendler's team, collaborating with the White House Data.gov staff, has developed smart interfaces that allow government data from an enormous variety of international sources to be combined in beneficial and unexpected ways. And so they've made it possible for others to do what's called a mashup, to mash up data sets and to develop over 1,200 applications in areas of health policy, transportation policy, and more. So this is just on our side. But if scientists could share their research data openly with colleagues across the globe, we could speed up innovation radically. And so Rensselaer Professor Francine Berman, for instance, is the US representative to what's called the Data Research Alliance, which is a new international organization formed to accelerate the ability of scientists everywhere to access, combine, and utilize each other's data. There are a lot of public policy questions embedded in this. So in the future, data discovery and exploration will be the foundation of many a career, and we feel a strong obligation to prepare our students in every discipline to collaborate in the use of high-performance computing, data analytics, the semantic web, and other interactive tools in order to maximize their opportunities to drive discovery and innovation. For example, starting this fall, the fall of 2013, we will be offering a new Master of Science degree in business analytics through the Lally School of Management and Technology. And under the new Rensselaer Plan, which John Dordick spoke about, we call it the Rensselaer Plan 2024 because it takes us up to our bicentennial. We're positioning Rensselaer for an even greater degree of leadership in this data-driven, web-enabled, supercomputer-powered, globally interconnected world. And with the Rensselaer Idea, we will no longer have a group of strong but separate disciplines. We will have a full data-driven ecosystem that is going to produce a range of discoveries and applications that will allow us to change the world. Again, the fundamental message, if we make intelligent use of the tools at our disposal, we can better model planetary systems or global systems relating to, for example, the flow of water or power, allowing better allocation of scarce resources. We can use predictive analytics to make better decisions in every field, assessing, for example, how a new nanomaterial is likely to behave under the kinetic conditions of manufacturing, or how to design new cities to make them as energy efficient as possible. The implications of such data-driven research are particularly important in healthcare. And our new partnership with the Icahn School of Medicine at Mount Sinai is going to bring together supercomputers and people at each of these entities that will allow us to produce sophisticated algorithms to analyze genomic data from many, many patients. We will be able to use that data to develop predictive models of disease, to develop more safe and more effective drugs, and to make better use of shared healthcare assets and scarce financial resources. And so as we grapple with other multifaceted questions such as climate change, its implications and solutions, Rensselaer work in web science and data visualization will help researchers to turn ecological and social and policy questions into big data questions and allow them to discover and visualize information that is both local and truly global in scope. We also have to be aware, and we know that from what we hear every day in the news, of the security and social challenges that these technologies present. And so the Rensselaer Idea will include public policy, and it will also include our Data Science Research Center, led by Bülent Yener, And that center is exploring cybersecurity issues ranging from better encryption algorithms to identifying malware via software signature data. But we also have to always look at the public policy implications. Ultimately, the goal of the Rensselaer Idea is to find ways to access and aggregate a global storehouse of social, cultural, financial, scientific, and engineering information, and then make it available in a form in which any person, anywhere on Earth, can ask important questions and contribute to emergent hypotheses. Now, we understand that one of the most crucial things that we can do here at Rensselaer, and we take it as our challenge, is to change the world for the better. But to do that, we have to shape the tools and make the breakthroughs that enable others. And so here at Rensselaer, we will address the hard problems, not the trivial problems, the hard problems, which we are uniquely qualified to address because of our strengths in engineering, in science, in design, in management and entrepreneurship, and in the humanities, arts, and social sciences. We are unique. We will continue to leverage our interdisciplinary approaches to problem solving and educating our students using the new tools and technologies in this, again, data-driven, web-enabled, supercomputer-powered, hyper-connected world, because we are Rensselaer Polytechnic Institute, and this is our big idea. Thank you very much.
Okay, thanks very much, Dr. Jackson. So now I do want to introduce the new, actually the first and only director of the Rensselaer Idea. As the president mentioned, Jim Hendler is the Tetherless World Senior Constellation Chair at Rensselaer, also the head of the Department of Computer Science. So Jim has authored more than 200 technical papers in areas of artificial intelligence, the semantic web, agent-based computing, web science, many others. He's one of the early developers of the semantic web. He's the editor-in-chief emeritus, you're emeritus of something, I guess, of IEEE Intelligent Systems, and is the first computer scientist to serve on the board of reviewing editors for science. So I know the president mentioned this, stole my thunder here. In 2010, he was chosen as one of the 20 most innovative professors in America by Playboy magazine. Now, I know that issue, Jim, must have been the one everybody looked at for the stories, right? Jim currently serves as an expert or an internet web expert for the U.S. government, providing guidance to the White House through the data.gov project. So everyone, please join me in welcoming Jim Hendler to the podium. No, you won't.
Thank you very much. You know, the way I like to say it is one of the things that got me to Rensselaer and has been really exciting about both coming here and in the past year looking at the refresh of the Rensselaer Plan is that plans and ideas go together. And we've been putting together this idea that Dr. Jackson has just told you a little bit about, and what I want to do is give you a little bit more about that. And I won't today talk in too much detail about how it fits in with the Rensselaer Plan refresh, but if you go, when you read that document, you'll see that this really fits very strongly into our strategic vision for the future of RPI. So I want, before I start, to say that I'm about to show you a lot of pictures of research. I'm about to talk about some research ideas. I want to make it very clear that these are ideas from researchers across the Institute. I don't have the time today to introduce everybody who's been involved in this. In the slides I have, they'll be too small for you to read, but they'll be going online, the names of the researchers who've done the different projects and things like that. So I just want to make it clear that this really is a campus-wide institute. You will be seeing things from all 5 of the schools at Rensselaer. You'll be seeing things from literally dozens of professors. There's also a lot of student effort. There's a lot of new projects going on. There's a lot of, this is just an exciting place to be. In fact, I'm gonna take 1 second of personal privilege and introduce my new Watson team. Guys, you wanna just quickly say hi? As Dr. Jackson mentioned, we're the first school to really be getting Watson in all of its forms to work with, and I just wanted you to see his classmates. So finally, I just want to say a minute before I start my talk, let me give you 1 second about what I want to do today, because I have a lot of slides, there's a lot of technical material, and what I really want to do is go through most of them Ignite style, the sort of Pecha Kucha. So you know, not talk about them much, just show them and hit 1 or 2 ideas in each. So I'm going to do a few slides in normal professor slide mode, trying to keep myself moving. But when I hit the technical slides, which could easily be an hour each, I've got a student who's going to start signaling me after 30 seconds if I haven't changed slides. So they're going to move very fast, and I'll share them with you later. So let's get started. So the idea that I've been playing with, sort of the metaphor, is we have these applications up here, which are the things in the world we want to fix, and we have a lot of data all over the place. And to put them together, we kind of build these thin little pipelines between them. So we're trying to reach down into the data, and we make up for each different application its own way of attacking this problem. And the problem with that is that these applications are very brittle. They are these, you know, it's like a forest of small trees. You really have to hope no strong wind blows. So they're complicated to develop, expensive to maintain, lots of other problems. And most importantly, from a university point of view, they lead to a lot of duplication of effort that at most places fall along the stovepipes between departments or between different parts of a university. What's great at RPI is we've really been a place which has always looked at interdisciplinary innovation, at bringing ideas from the lab to the product, from one part of the university to another part. And what we want to do now is start in the data space, really looking at a different way to do this. And that's, I'm going to use this so looking at some data. When you look at a tree and why trees fall down, I found the International Tree Failure Database. So this had to be a data-driven talk. And it says there's really 3 parts of your tree that can cause it to fall down. This will be very exciting to you all. Trunk, branch, and root. There's not much else. So what I want to do is actually say what we're trying to do at Rensselaer is build the tree right, is make it so that those branches at top are big and thick and shared, that they come down into a trunk which utilizes the unique capabilities we have here at Rensselaer, but not separately and not in stovepipes, but all in one place. So we're looking at how we're going to take the high performance computing, the data science, the predictive analytics, the cognitive computing, the things we can do in a performance center like this, and pull it all together so that a researcher coming to do a data-driven application doesn't start from scratch. They have tooling and they have infrastructure across all of those things. And then, of course, we want to build some tools that make it much easier to get at and manage what's down at the data level. Dr. Jackson showed you a version of this slide. I've just made, tried to a little more clearly delineate what are some of the real resources we have here, like MPAC, CCNI, and the Watson project, which really give us large-scale platforms to work on, and then all the other things going on RPI, centers, constellations, et cetera, which IDEA will be looking at. How do we bring the people together? How do we make this all work? Okay, so here's where we're going to go into the fast mode. Okay, so I'm going to go quickly through from the top of the tree down, looking at some of the applications. Dr. Jackson already mentioned these areas. So here's just a couple of examples. This is some work that was done by my colleague Deborah McGinnis, looking at smoking data and at which kind of interventions by a government have the highest impact. But what's interesting about this is that the National Institute of Health has been pulling this data from lots and lots of places in lots of ways for a long time. We pulled it all in one place. It was able to show some really interesting results. In fact, it wasn't what was expected. I'll let Deborah tell you the results later if you want to hear them. We're looking at smart and built environments. So this is just a slide from some work done by my colleague Jose Joaquin-Veras. And this is looking at how, this is just one example. They're just looking at the park and ride situation in New York. But he pulled data from all these different places, was able to create an analytic model of what was going on. It can be used by urban planners. It can be used in exciting new ways to really do something different. Now, it has at its heart now an equation that talks about particular urban features. We'd like to know, does that same equation work for other parts of the world? You know, can we do other applications with it? We're looking at network science and cybersecurity, as was mentioned. This is some work by Bolek Szymanski at the NET Center and a number of other colleagues, and some work Deborah and I and others are doing around campus. So this is really something we're seeing a lot on campus, which is people have talked for a long time about using social media, but how do we use it to do something important, right? How do we use it to help solve security problems? How do we look at threats to society across a wide network of the threats and say how they respond to each other? How do we take the millions and millions of tweets that we can collect literally in days and use them, for example, for first responders or for people looking at trends around the world to analyze what's going on? This is some work that's going on. Peter Fox heads this one up. This is looking at the Deep Carbon Observatory. This goes way beyond RPI. This is a project which Sloan mostly is funding, has researchers at dozens of different schools, hundreds of databases involved. And what we're talking about here is carbon. Just to remind you of the importance in carbon on our world, we're made of it. We burn it to power systems. We're doing it. Looking at carbon across all the different things it does, from deep in the ocean to in lava to in us, takes a major amount of data innovation. And Peter and others have been looking at how do we build a platform to make it so all those scientists can share data across those many fields and domains. Well, how do we do that here? How do we start taking that platform to something that every kind of science can use? That can be done in many different ways. So that's just an example of some of the things up at the top. Let's look at the trunk. And we mentioned already some of these different capabilities we have in some of the places on campus. So with the high performance computing, we can do all sorts of simulation and modeling, but we're also looking at building tools, both discrete simulation and continuous simulation, where we can really look at what are the key features of taking data into a supercomputer like that and making it usable. What are some of the different kind of things? And just, I have 6 random pictures here. They're from 5 or 6 different fields, and we have dozens of pictures of things that have gone on at our CCNI from all over the campus. We want to start making some infrastructure that makes it even easier for campus researchers who want to do a new data-oriented thing to use that facility. I'm not even going to try to tell you all the things on this slide, but this is, we mentioned before, the Data Science Research Center. This is a really critical thing. Data, it's easy to think about it as just a bunch of numbers sitting in some kind of spreadsheet somewhere. But in reality, the algorithms for interacting with it, the ways we generate it, how we filter it, how we look at it, how we use it, is a hard and complicated growing scientific area in its own right. We have a team of people from around campus involved in this data science center, which will be part of the idea, just really bringing together that work so that other people who are looking to find a new way to analyze their data, a new way to use their data, can do it. Cognitive computing, we mentioned Watson, but we really want to go not just Watson, but Watson beyond. So Watson gives us a great way to pull in unstructured data, the data that's in text, the data that's out there in the web that's not in those nice, neat boxes or not in traditional analytic forms. But having got that data, what do we do with it? We have many different kinds of cognitive computing we've been looking at campus. Can we pull those things together? Can we make that something so that a researcher who doesn't understand language processing or doesn't know the pipeline underlying the Watson project can use that kind of technology to help them solve real-world problems? Finally, I want to say, you know, when we think about using a space like the one you're in today, right? We're sitting here looking at slides at the front of the room. What a crazy way to use this space. We have speakers all over the place. We could be doing sonification. We have visual cues in color, in shape, in size. We have lighting. You know, this stuff could be changing colors to mean things. How do we use that to interact better with data? How do we look at data change over time? This is a project Erica Mires, who's both a graduate student and one of the people who helped make this center run, is looking at, you know, can we take how data changes over time in many of these different models and start looking at how we can see and understand and perceptualize and work with that, okay? Finally, moving down to that pool of data at the bottom, I like to use the acronym dive into data. I also couldn't resist because I found a great quote in Geekopedia, which I won't read to you. But it was just the existence of Geekopedia that I couldn't resist, which is, you know, you've seen plenty of things that describe things that real people in the world want to know, but this is the very narrow stuff that only us geeks really want to do. And their definition of data exploration, which is one of the real themes of this, says, you know, it's about getting the right kind of data at the right kind of ways to the right kind of applications, using it efficiently, et cetera. So how do we discover data? How do we integrate data from many different sources? How do we validate that the models we've built off of data actually make some sense? The more data you have, the easier it is to get spurious computations. If you're doing traditional psychological work, you try to get 1 in 20 probability. Well, run 50 examples and you'll get a 1 in 20 somewhere in there, right? You'll get 2 or 3 of them, but get it right. How do we adjust the numbers? How do we get them right? How do we check data against other data? Finally, Dr. Jackson mentioned the sharing of data. A prototype project that's been done over the past couple years here at RPI has been data.rpi.edu, where we're trying to take some of the data collections and data resources of the university, make them available not just to our own researchers, but to everyone. We're going to be relaunching that project under IDEA with a lot more power using some of the things we've talked about and with a lot more data in it, so that when a researcher wants to tell other people about what data they have or wants to find data that someone else has, we have a single shopping place to go. You'll come to this site, you'll work through it, and you'll be able to find the kind of data you're looking for. So again, building that ecosystem. We want that really strong tree all the way from the applications down to the bottom. So to summarize, the Rensselaer Idea is pulling together all these data technologies. We want to allow researchers to discover or develop or derive whatever data they need using all these different sources and all these different tools. We want to be able to process that data through multiple pathways, allowing new analytic insights. We want to provide new cognitively informed ways for dealing with that unstructured data rather than expecting ad hoc ways by each and every researcher who wants to touch text. We want to validate the data. We want to look at tools to analyze, explain, visualize, repurpose, store, cite, share, catalog, stream, scrape, supply, and I'm sure I'm leaving out another 20 adjectives I could have come up with. But it's all there. This data stuff has become really crucial. So in our innovation technology, in our approach at RPI to taking things all the way from basic science out to the real world, understanding them across the board, we really want this data stuff to drive what Rensselaer is really known for, which is the kind of innovations and applications that can change the world. Thank you.
Well, thanks a lot, Jim, giving us a lot to think about, obviously. But before we end today, there's an opportunity for the media to talk to Jim, to the president, to myself, if anybody is interested in that, as well as for a broader discussion if we'd like to have one. But right now I'd like to give an opportunity for our students and our faculty to ask questions. And if you have any questions, the microphone is over here on my right. So if there's anyone interested in asking anything, come forward. I guess things were just so perfectly clear. Anybody have any ideas? That was bad. Okay. So, you know, let me just say, again, thanks for everyone to be here today. We very much appreciate this. We will, though, have a much more substantial formal launch of the Rensselaer Idea that will occur sometime in the fall with a symposium and a number of other activities that will really help show what the idea is and where it's going to be going. But for now, let's come together. We have a small reception, 1 floor up on the 6th floor here at MPAC, so I welcome you to join us for that. Thanks very much.